Good day, esteemed researchers and curious minds tuning in from around the globe. We're here to delve into Galactica, a large language model for science, a groundbreaking study that challenges traditional methods of accessing scientific knowledge. This research explores the potential of language models as innovative tools for literature exploration and scientific discovery, offering intriguing insights into their capabilities beyond text-based tasks. Stay tuned as we unravel the fascinating journey of Galactica, a model that's reshaping the landscape of scientific knowledge access and application. The traditional method of storing and retrieving scientific knowledge has its limitations. It relies heavily on human effort for reasoning, combining, and organizing information, leading to a significant bottleneck in knowledge throughput. Language models, on the other hand, have shown promise in tasks like citation prediction and knowledge-intensive question answering. However, these models still need architectural changes to perform tasks in the same way humans do. Our research proposes a new approach. We suggest using language models as a tool for exploring literature and the vast body of scientific knowledge. We've used a working memory token approach, which has shown strong performance on mathematical benchmarks. Furthermore, we've trained our model to act as a bridge between scientific modalities and natural language, opening up new possibilities for knowledge absorption and retrieval. Our research has yielded some key technical results. Firstly, we found that our language model surpasses retrieval pipelines in predicting citations. This suggests that language models could be a valuable tool for exploring scientific literature in the future. Secondly, our language model demonstrated strong performance in tasks that require intensive knowledge, such as question answering. It was able to compose a curated knowledge base and reason in a step-by-step manner, outperforming existing methods on mathematical benchmarks. Lastly, we've seen promising potential in tasks like automatic protein annotation and drug discovery. For instance, our model, Galactica, was able to learn tasks like IUPAC naming through self-supervision and formulate drug discovery tasks in a natural language prompt, achieving strong results without direct fine-tuning. These findings highlight the potential of language models in tackling knowledge tasks that are currently human specialisms. For many decades, the primary method of accessing scientific knowledge has been a store and retrieve system. This approach, while effective, heavily relies on human effort to reason, combine, and organize information. This reliance creates a significant bottleneck in knowledge throughput. The image here illustrates the concept of multimodal data, a key element in our research. We're exploring how language models might disrupt this traditional paradigm, potentially paving the way for a more efficient interface for humanity to interact with knowledge. We propose a novel solution to the knowledge throughput bottleneck: language models. These models aim to disrupt the traditional store and retrieve paradigm, creating a new interface for accessing knowledge and reducing our reliance on human effort. The problem we face today is a bottleneck in knowledge throughput, caused by the traditional paradigm that limits the speed and efficiency of accessing scientific knowledge. To address this, we've introduced an innovative approach: the working memory token. This tool has been used to achieve strong performance on mathematical benchmarks and has significantly improved our problem setting. This is a step towards a future where language models take on knowledge tasks that are currently human specialisms. Language models have shown remarkable strength in absorbing technical knowledge, even to the point where they can potentially take on tasks that are traditionally human specialisms. However, a significant bottleneck we face is the availability of high-quality datasets. To overcome this, we propose using language models that can effectively learn from the available data. In our training process, the model acts as a bridge between scientific modalities and natural language. It learns tasks like IUPAC naming through self-supervision, demonstrating its ability to acquire complex knowledge. Furthermore, we found that it's possible to formulate drug discovery tasks in natural language prompts, which the model can then process and learn from. This approach opens up new possibilities for how we can leverage language models in scientific research. Our research proposes a novel approach to harness the power of language models for scientific exploration. We've found that these models can serve as robust tools for delving into scientific literature, absorbing technical knowledge like LaTeX equations and chemical reactions. We've also developed a working memory token approach that has shown promising results on mathematical benchmarks, outperforming existing methods. This approach allows the model to perform knowledge-intensive question-answering tasks in a step-by-step reasoning manner. Furthermore, we've trained our models to bridge the gap between scientific modalities and natural language. For instance, we've demonstrated that tasks like IUPAC naming can be learned through self-supervision. Lastly, we've been able to formulate drug discovery tasks in natural language, achieving strong results without direct fine-tuning. This opens up exciting possibilities for automating complex tasks in the field of drug discovery. In essence, our research is pushing the boundaries of what language models can achieve in the realm of scientific knowledge exploration and application. Our research presents a detailed methodology that employs the transformer architecture, known for its flexible weight memory. We've introduced an element of randomness in the order and format of training, and we've also been careful to train on a small subset of entities to avoid any bias. In terms of problem formulation, we're challenging the traditional store and retrieve paradigm. We aim to overcome limitations such as the heavy reliance on human effort in current models. We propose language models as a new interface for knowledge access, a shift that could revolutionize how we interact with and utilize information. This approach has the potential to make knowledge access more efficient, accurate, and user-friendly. In our research, we've conducted a series of experiments to evaluate the performance of language models on tasks such as citation prediction, question answering, IUPAC naming, and drug discovery. We've also compared our methods with existing ones on MMLU and math benchmarks. A key technique we've used is the working memory token approach, which has shown strong performance. On the technical side, we've proposed improvements to the methods. We believe an architectural change is needed for adaptive computation, which will allow language models to perform tasks more like humans. We've also utilized the transformer architecture, known for its flexible weight memory. This has proven effective in absorbing large bodies of scientific knowledge. This combination of experimental design and method improvements is what drives our research forward. Our research has yielded some key results that we're excited to share. Firstly, we've seen superior performance in citation prediction, where our language model outperformed both sparse and dense retrieval pipelines. This is a significant achievement in the field of information retrieval. Secondly, we've demonstrated strong performance in knowledge-intensive question-answering tasks. Our model surpassed existing methods on mathematical benchmarks such as MMLU and math, showcasing its ability to absorb and apply complex technical knowledge. Thirdly, we've explored the potential of our model in tasks like automatic protein annotation and drug discovery. We've been able to formulate these tasks in a natural language prompt and achieve strong results without direct fine-tuning. This opens up exciting possibilities for the application of language models in scientific research. The implication of these results is profound. Language models can be effective tools for exploring literature and scientific knowledge, and can potentially take on knowledge tasks that are currently human specialisms. This could revolutionize the way we access and utilize knowledge in the future. As we conclude, let's reflect on the transformative potential of language models. They have the capacity to revolutionize the traditional store and retrieve paradigm of accessing knowledge. As we can see in the figure, Galactica's citation distribution closely mirrors the ground truth, especially as the scale increases. This indicates its superior performance in citation prediction. Furthermore, language models have proven to be powerful absorbers of technical knowledge, with their capabilities scaling smoothly with model size. This suggests a promising future where language models could become a new interface for humanity to interact with knowledge, disrupting current human specialisms. Our research has shown that language models can outperform retrieval pipelines in several areas. They excel in citation prediction and can compose curated knowledge bases for knowledge-intensive tasks. We've introduced a working memory token approach that achieves strong performance on mathematical MMLU and math benchmarks. Moreover, we've made strides in bridging scientific modalities and natural language. Tasks like IUPAC naming can be learned through self-supervision. Even complex drug discovery tasks like molecule net can be formulated in natural language prompts. In essence, we're pushing the boundaries of what language models can do, and we're excited about the potential they hold for the future of scientific research. Language models have shown immense potential in taking on knowledge tasks that were once exclusive to human specialists. They are emerging as valuable tools for exploring literature and the vast body of scientific knowledge. However, we face challenges. The availability of high-quality step-by-step datasets is a bottleneck that needs to be addressed. Additionally, to perform tasks like humans, language models require architectural changes that support adaptive computation. But the scope of language models is not limited. They hold promise for tasks that bridge scientific modalities and natural language, extending beyond just text-based tasks. This opens up exciting new avenues for their application in diverse fields. As we continue to explore and expand these capabilities, we look forward to witnessing the transformative impact of language models on our understanding and interaction with knowledge.